Hello everyone. So today we are going to discuss about the module 2, that is module 2, which consists of 4 different topics. The first topic, that is Mosfet amplifier configuration, that I'm going to discuss today. So module 2, in module 1 we have studied the various concepts under Mosfet, right? So today we are going to see the amplifier configurations, that is the contents included in module 2, that is the first topic. Mosfet amplifier configurations are basic configurations, that is similar to your BJT, bipolar junction transistor. Even your MOSFET has also got the various configurations. So in BJT we have studied 3 different configurations: common emitter, common base and common collector, whereas here we are going to see similar to that 3 configurations are there, and then we are going to study in detail common source amplifier without source resistance and with source resistance, and then we are going to study about one more configuration, that is source follower, or it is also known as common drain, then MOSFET internal capacitance and high frequency model. So out of which we are going to study initially the basic configurations. Okay, similar to BJT, as I told, 3 configurations are there. Now there are 3 configurations, basic configurations for connecting the MOSFET as an amplifier. So each of these configurations, similar to BJT, is obtained by connecting one of the 3 MOSFET terminals to ground. Okay, that is, either we know the terminals of the MOSFET: source, gate and drain. So out of these 3 terminals, one of the terminal will be grounded. So based upon that, the configurations it is being done. So thus creating and thereby it is going to create a 2-port network with the grounded terminal being common to input and the output port. So the 3 configurations are common source, common gate and common drain. In a sense, here the source terminal is grounded, here the gate terminal is grounded, and here drain terminal is grounded. In a sense, here source terminal is common for input and the output, here gate terminal is common for input and the output, here the drain terminal is common for input and the output. Okay, so out of which the first configuration is common source amplifier or CS amplifier. So this is a picture which depicts common source amplifier, common source configuration. So symbol of FET, you know it is, this is a gate terminal, drain and the source terminal. Source terminal is grounded. So to the gate terminal we are providing the input, that is Vi, it is given to the gate terminal, and from the drain terminal we are taking the output. In a sense, here input we are applying across gate and the source, the input to the gate with respect to source, and then output we are taking across drain and the source. So across this the drain resistance it is being connected, that is RD. So across RD we are going to get the output voltage. So in this circuit, the source terminal is connected to the ground. The input voltage signal, that is Vi, is applied between the ground and the gate, and the output voltage signal is taken between the drain and the ground, or drain and the source across the resistance RD. This configuration, therefore, it is called grounded source or common source amplifier. It is by far the most popular MOS amplifier configuration. Similar to common emitter, common source, it is a most commonly or widely used configuration. So the next configuration is common gate amplifier configuration. So you can see in this picture, gate terminal is grounded, whereas source terminal we are providing the input Vi, and from the third terminal, that is drain terminal, we are taking the output. So across RD we will be getting the output voltage. So such type of configuration we call it as common gate or grounded gate amplifier configuration. So this is being obtained by connecting the gate to ground, gate terminal is grounded, applying the input Vi between the source and the ground, and taking the output across the resistance RD, which is connected between the drain and the ground. And the last one is common drain configuration. It is also known as grounded drain amplifier. As you can see in the figure, the third terminal, that is drain, is grounded, and to the gate we are providing the input, and from the source we are taking the output. To the source terminal, the load resistance, it has been connected, across which we are going to obtain the output. So it is obtained by connecting the drain terminal to ground, applying input voltage signal between the gate and the ground, and taking the output voltage signal between the source and the ground across the load resistance. So for reasons that will become apparent shortly, this configuration is more commonly called as source follower. So what is the one more name for common drain? So it is called source follower. Okay, source follower. So we have seen common drain, common gate, and common source configurations. Now let us see the next topic, which is very important, that is characterization of the amplifier as a functional block. So before we begin our study of different MOSFET amplifier configurations. That is, in detail, if we go for common source, common gate, or common drain, before studying these configurations in detail, we consider how to characterize the performance of an amplifier as a circuit building block, So an introduction for this topic is presented over here. So this has been introduction, how the amplifier acting as a functional block. Okay, so this figure, the first figure which shows, it is an amplifier which is fed with the voltage signal, that is V subscript signal, having a source resistance, that is R signal, it is a signal resistance, and feeding load resistance RL. So this is an amplifier to which we are providing the signal V signal, which is having a internal resistance of R signal. The current flowing to the amplifier is II, and current coming out of this is I naught, and across the RL we are going to get the output. So which is having a signal source, open circuit voltage V signal, and an internal resistance R signal. These can be the parameters of an actual signal source, or in cascade amplifier, the Thevenin equivalent of the output circuit of another amplifier stage preceding the one under study. So this is the one of the circuit which is under study. Similar to this, one more amplifier will be connected. Such type we call it as cascading. Okay, so the amplifier shown with the load resistance RL connected to the output terminal. Here RL can be an actual load resistance or the input resistance of a succeeding amplifier stage in a cascade amplifier. Okay, so this is the first figure we have seen. Now in detail we shall see this figure, that is how this amplifier, it looks at the input side and at the output side. That is a hybrid pi model we are going to see in the next thing. So the figure B, this is an equivalent circuit representation of the first figure. So the amplifier, that is a amplifier part, it has been in detail given. It is amplifier having the internal resistance R in, voltage across that is VI, and at the output side we are going to get the amplified signal, that is AV naught into VI, and output resistance in series. Okay, rest all it is same as that of the first circuit. So the figure B shows amplifier circuit with the amplifier block replaced by its equivalent circuit model, that is a hybrid pi model. The input resistance represents the loading effect of the amplifier input on the signal source. So the input resistance, because of this, it doesn't have any loading effect. Okay, so it is found from, that is R in. How we can calculate this is, that is voltage across this, and what is the current flowing? It is II. So VI divided by II, and together with the signal resistance R signal forms a voltage divider that represents V signal to the value VI that appears at the amplifier input. That is, what is the amount of VI that can be calculated with the help of voltage divider rule. That is, this V signal, it has been divided between two resistances, that is R signal and R in. We are interested in calculating VI, that is the voltage across the input resistance of the amplifier R in, So what is the voltage across this? That is nothing but R in divided by the total resistance, R in plus R signal, that into V signal. Okay, so R signal into V signal, R in plus R signal into V signal. So all amplifier circuit, whatever we have studied till now, these are unilateral. Unilateral means that is they does not contain internal feedback, and thus your R in internal resistance of the amplifier will be independent of your load resistance. See, there is no connection. These are all unilateral. There is no feedback network. So that is why your R in will be independent of RL. Next circuit, next is the and here we need to know different parameters. See, while considering any amplifier, three different parameters are: one is the input resistance, one is the gain, and next is the output resistance. So input resistance we have calculated is VI by II. VI can be calculated using voltage divider rule. So the next parameter is gain, that is the open circuit voltage gain AV naught, that is this one, AV naught, open circuit voltage gain. How this can be calculated? That is V naught divided by VI by considering RL at infinity. So this condition is very important. By considering RL at high value, very large value, what is the open circuit voltage gain AV naught. Next is the third and the final parameter, that is the output resistance R naught, which can be calculated like Vx divided by Ix, that is depicted in the figure C. That is, output resistance can be calculated by considering the input voltage as 0, Vi as 0. So what happens to your output side of the amplifier? This will be 0. So how we can calculate R naught? R naught is nothing but one test voltage will be applying over here, that is Vx, that divided by Ix. This is derived from the test voltage Vx. So R naught is nothing but Vx divided by Ix. Okay. So this is the output resistance formula. By considering input voltage as 0, you will be calculating the output resistance. So which are the three parameters we need to know while studying the amplifier as a functional block is? One is the input resistance R in. Okay. Next is the open circuit voltage gain, and next is the output resistance R naught. Okay. Next, the controlled source AV naught into VI. This is a control source. You see, this is the controlled source AV naught into VI, and the output resistance R naught represents the Thevenin equivalent of the amplifier output circuit, and the output voltage V naught, it can be found from, see here, the V naught can be found from, how we can calculate V naught? V naught is nothing but voltage across the resistor RL. So this I naught, it is divided across R naught and RL. So it is nothing but RL divided by R naught plus RL into AV naught divided by VI. Okay, see here, V naught is nothing but RL divided by RL plus R naught into AV naught into VI. So how we can calculate the gain V naught divided by VI? This is the voltage gain of the amplifier, not the entire circuit voltage gain. This is the gain of the amplifier. Gain of the amplifier V naught divided by VI, which is nothing but RL by RL plus R naught into AV naught. AV naught is the open circuit voltage gain. Okay. Next, overall gain, it has been represented, voltage gain, it is represented by G subscript small v. This is nothing but output voltage V naught divided by the signal applied to the amplifier, that is V signal, Mosfet. Okay. So this can be determined by using the two equations, that is, one is V signal, this one VI, using this, and using this equations. So what is V naught? V naught, see, V naught by V signal, how I can write this as V naught by VI into VI by V signal. Okay, that can be obtained from these two equations, that is AV equation and then this equation. VI equation. See, VI by V signal we can obtain from this. So this is VI by V signal we can obtain from that, and V naught by VI, it is nothing but AV naught into RL by R naught. See here, AV naught RL divided by RL plus R naught, and this is nothing but V naught divided by VI divided by V signal. That is Rin divided by Rin plus R signal. So this is regarding the amplifier considering as a functional block. Now, next let us study one of the configuration, that is the first configuration, most widely used configuration, common source configuration, common source amplifier. Okay, so now this is the circuit we have seen initially. So the signal will be applied to the gate terminal, source terminal will be grounded, and output across the drain resistance we will be taking. Okay, so input resistance at the input side of the amplifier, output resistance taking at the output. So here the signal applied is V signal, and this is the internal signal resistance of the signal. Okay, output resistance, output voltage. So in detail, the second circuit which depicts the equivalent circuit model of common source, that is a hybrid model. So here why your resistance R in is not mentioned is it will be ideally very high value. Okay, so what happens here, the circuit accepts the V signal, that is signal voltage. Signal will be applied between the gate and the source. Between the gate and the source, the signal will be applied, and it provides current. It provides the current of GM into VGS at the drain terminal. So this is the current at the drain terminal. So the input resistance of this controlled source is very high. Okay, that is ideally infinite. That is why here it is not, they have not shown the symbol of the resistance, because it indicates that R in input resistance is very high. It is ideally infinite. Okay, so the first figure which depicts common source amplifier with the biasing arrangement is omitted, in the sense, of course, here along with this the biasing voltages will be there, that is not shown over here. So common source amplifier fed with the signal source V signal having a source resistance R signal. Then we wish to analyze this circuit to determine, as I told, there are various parameters are there, that is the input resistance and the open circuit voltage gain, output resistance and the overall voltage gain. For this purpose, we shall assume that RD, that is the drain resistance, is a part of the amplifier. Thus, if a load resistance RL is connected to the amplifier output, it appears in parallel with RD. See here, shown here, RD is considered. So in order to calculate the output resistance, what happens? Output resistance is nothing but RD, which is connected in parallel with R naught. So if load resistance is connected, even that will be considered as in parallel with these two resistances, that is RD and R naught. Okay, so characterizing parameters of the CS amplifier, that is we need to determine what is the input resistance R in, what is the voltage gain, open circuit voltage gain, what is the output resistance, and what is the overall voltage gain. So for that we need to know this model, hybrid model of CS amplifier. R in input resistance is infinite, as we have got to know. In input resistance it will be infinite ideally. So next is output voltage is found by multiplying the current GM into VGS by the total resistance between the output node and the ground. Okay, so V naught, which is nothing but minus GM into VGS. The action of the current is reversed over here. That is why the minus sign, minus GM into VGS into what is the resistance? R naught. R naught is nothing but RD parallel to R naught. RL is not considered over here. So R naught, output resistance will be R naught parallel to RD. So the output voltage equation is this one. since VGS is equals to VI, in the sense whatever the gate to source voltage we are applying, voltage between the gate and the source, it is nothing but the input voltage of the amplifier VI. So that is the open circuit voltage gain. AV naught is nothing but V naught divided by VI. It can be obtained as, that is from this V naught taking VGS to the other side. VGS is nothing but VI. So V naught by Vi, which is nothing but the open circuit voltage gain, which is equals to minus Gm into Rd parallel to R0. So now we have got two parameters out of 4, that is Rin as infinity and Av naught as minus Gm into Rd parallel to R0. Rd parallel to R0. So yeah, now Rd is lower than R0, and effect of R0 on reducing AV0 is slight, that is less than 10% or so. Thus, in many cases, we can neglect R0 and express AV0 simply as this much. That is, R0 we are going to neglect over here. That is, especially in the discrete circuit design, we are going to neglect this resistance R0 because it is very much smaller than RD. So we are going to neglect this R0. So almost the voltage gain, open circuit voltage gain, it will be on approximately equals to minus Gm into Rd. The small R0 doesn't going to affect your voltage gain, open circuit voltage gain. Next thing is we need to calculate the output resistance. Output resistance we know, output resistance, that is Rd parallel to R0. So R0 is a resistance seen looking back into the output terminal with the Vi set to 0. That is what the procedure. Output resistance will be calculated by considering Vi this as 0. If this is 0, what will be Gm into VGS? This will be 0. So finally we will be getting these two resistances in parallel, that is nothing but R0. VGS will be 0 and thus Gm into VGS will be 0, resulting in R0 is equals to Rd parallel to R0. Since we know R0 is very much lower than Rd, so R0 will be approximately equals to Rd. So the last one is remaining, that is, let us see later, that is the voltage gain GV. So this particular section, which concludes the analysis of CS amplifier proper, we can make a note now. That is, following observations we can make it out. Initially, the input resistance, that is Rin, which is ideally infinite, and the output resistance is moderate to high, that is in the kilo ohms to tens of kilo ohms range. This reducing to lower is not a viable proposition since the voltage gain is also be reduced. Okay, so that is why it is moderate to high. Alternatively, if a low output resistance is needed, a source follower stage is considered. Next, the open circuit voltage gain can be high, making the CS configuration a workhorse in the MOS amplifier design. Unfortunately, however, the bandwidth of the CS amplifier is severely limited. So this particular thing, that is the bandwidth of CS amplifier, you are going to see later. So these three observations we can make it out. That is, Rin is infinite, output resistance is moderate to high, open circuit voltage can be high. And the last one is the voltage gain, overall voltage gain GV. So to determine GV, we first note that infinite input resistance will make the entire signal, V signal, appear at the amplifier input. That is, your input to the amplifier, which is nothing but the signal voltage applied. An obviously ideal situation. This will be an obviously ideal situation, not the practical one. At this point, we should remind the reader that to maintain a reasonably linear operation Vi, and hence V signal should be kept much smaller than 2 into VOE. What is VOE? It is nothing but the overdrive voltage. I hope you know what is this overdrive voltage. So what we are doing is, in the ideal situation, that is V signal, that is a signal voltage, that should be kept much smaller than 2 times the VOE. Okay, so if a load resistance RL is connected to the output terminal of the amplifier, this resistance will be in parallel with RD, that is RL will be parallel to RD. It follows that voltage gain AV can be obtained by simply replacing RD in the expressions AV naught. That's it. So this expression already we have got RD parallel to R naught, that will be connected parallel to RL if RL is considered. Okay, so this expression together with the fact that Vi is equals to V signal provides the overall voltage gain, that is GV is equals to minus GM RD parallel to RL parallel to R naught. Whereas AV naught open circuit voltage gain is minus GM into RD parallel to R naught. But here we need to consider the load resistance also, because AV naught is different, AV is different. AV is the voltage gain of the entire circuit common source amplifier, whereas AV naught is the open circuit voltage gain. Yeah, and then performing the analysis directly on the circuit diagram. So this performing the analysis directly on the circuit diagram with Mosfet model used implicitly over here, that is R naught. See how it is connected here, and current is 0 means resistance will be high, so Rn is infinite. Okay, so VGS is Vi here. This is the amount of current we are going to get minus Gm into VGS, and output across the drain resistance V naught. So V naught is nothing but minus Gm into VGS RD parallel to R naught. Output resistance is RD parallel to R naught. VGS, or which is equals to Vi, which is nothing but input signal. This is what we need to know. So while drawing the figure, all these parameters you should mention. Next is one of the problem it has been discussed over here. So whatever the circuit diagram we have considered, this is without considering the source resistance Rs. Okay, common source amplifier without considering the signal resistance, source resistance Rs. So here a common source amplifier which utilizes a Mosfet biased at ID is equals to 0.25 milliampere with VOV which is equals to 0.25 volt and RD drain resistance 20 kilo ohm. So device has VA which is equals to 50 volt. VA is nothing but the voltage across this. Okay, that is 50 volt, and the amplifier is fed. Amplifier is fed with a source having R signal is equals to 100k and a 20 kilo ohm load RL is connected to the output. Find R in AV naught, R naught, AV and GV. Input resistance of the amplifier, open circuit voltage gain, output resistance, AV and GV. Overall voltage gain of the amplifier. Okay, and then if to maintain reasonably linearity, the peak of the input sine wave signal is limited to 10% of this much. What is the peak of the sine wave voltage at the output we are going to calculate. So out of these five, the first parameter, that is the input resistance, we know current is 0, that is why ideally it is infinite. This is the first answer. Rin is equals to infinite. And how to calculate AV naught? So in order to calculate AV naught, we need to know transconductance GM. In order to calculate transconductance, I need to know what is R naught, because I'll tell you what is this. We need to calculate V naught, R naught. So small r naught is nothing but voltage across that divided by the drain current. The current flowing there is drain current. So it is VA divided by ID. VA, which is given in the problem, 50 volt. That divided by drain current is also given 0.25 milli. If you substitute that, you will be getting the answer as 200 kilo ohm. Okay, 200 kilo ohm. Next is GM, transconductance you need to calculate. The formula to calculate the transconductance is 2 into ID divided by VOE. ID is given, VO is given. Substitute that, you will be getting the answer as 2 milliampere per volt. Next is voltage gain. So open circuit voltage gain, that is nothing but minus GM into RD parallel to R0. R0 we have calculated. This RD is given in the problem. GM we have calculated. Substitute that. You will be getting the answer as minus 36.36. Okay. Next you need to calculate the output resistance. Output resistance is nothing but RD, drain resistance parallel to small letter R0, output resistance of the amplifier. So which is equals to 20k. This we have calculated 200k. Substitute that, you will be getting the answer as 18.18 kilo ohm. Okay, moderate to high it is. In terms of kilo it is. So next is AV. AV is nothing but GV, voltage gain. So which is, there is a formula minus GM RD parallel to R0. Along with that RL will be considered because this is the overall voltage gain. This is the open circuit voltage gain. So RL is not there here. This is the overall voltage gain. So RL should be included. Only that is a change. So what is the AV? You will be getting minus 19.05. So overall voltage gain will be lesser than the open circuit voltage gain. Okay. So next, the last condition they had given, that is, if the input sine wave signal is limited to 10% of 2 into VOE, what is the peak of the sine wave voltage? What is V0 you are going to calculate for VGS limited to 10% of 2 into VOE. So what is VGS input voltage you need to calculate? That is 0.1 into 2 into 0.25. 0.1, 10% of 2 into VOE. VOE means 0.25 we have considered. If that reduces to 10% of 2 into VOE, this is the voltage, input voltage. For this input voltage, what is the output we are getting? That is nothing but AV into VGS. What is AV? Minus 19.05 into 0.05 means this is the peak signal for 10% reduce in the gate to source voltage. I hope this is understood. Very easy. You should know the formulas here. That is, this will be constant of course for common source without source resistance RS. So R0 will be VA divided by ID, this formula. Next is GM is equals to 2 into ID divided by VOE. AV0 is minus GM into RD parallel to R0. R0 is RD parallel to small letter R0. Next is the overall voltage gain GV or AV, which is nothing but minus GM into RD parallel to R0 parallel to RL. Next is 10% reduction in VGS. What happens to your output signal voltage? Okay, thank you. See you in the next session.